Okay,
This
so
call is now being
yeah,
recorded.
that's the recap. We have a physical quantity, which is basically everything that exists. It can be described by physical quantities, and then these physical quantities can be divided into a vector and a scalar. And we have scalars which only have magnitude but no direction. And we made example of mass, temperature, and so on. Then we have vectors. A vector has both magnitude and direction. And we said a vector can be typically represented using an arrow. So the arrow has length, which is our magnitude, and then it points to a certain direction. So hence it's a vector. And then we have a resultant vector, which is a sum of all the individual vectors. Now, so we ended up doing problems, right? So we'll just go straight to those problems. And then, last point, we said vectors can point in any direction and have any magnitude. And they can be of any magnitude. Right. So that's what vectors can do. So this is one of the shortest sections you will see in physics. Should be covered in actually one lesson. Right. So now let's move on to typical examples. Right. So last time we did a few. I think we did 2 examples, if not one. So now we'll do a bit more so you can see what it means to add vectors and have scalars and so on. So let's start with this one. We have a man pushes a cart with 10 newtons to the right. So you see a vector is always specified using a direction. 10 newtons, that's the magnitude, to the right, that's the direction. Right. So you never just specify it by magnitude and not direction. If you do that, it means what you're saying to us is that is a scalar and not a vector. Right. So always keep that in mind. As soon as you see to the right, to the left, just know you're dealing with vectors. Right. So this guy pushes a cart with 10 newton to the right, and then friction pushes back with 6 newton to the left. Right. So these are our magnitude. In red, we have magnitude, and in purple, we have direction. So now we are told to use the tail to head and the algebraic method to determine the resultant force. Right. If you remember, we said this is our tail, right? That's the tail. And we said this is our head. And we said resultant. Whenever you draw a resultant, is always drawn from the tail of the first vector, because you had this. If you remember very well, we would have something like this. Right, tail of the first to the head of the last. But we'll show you now. Tail of the first vector to the head of the last vector. This is the rule of the tail to head method, which is the graphical method. So graphical means you're just drawing stuff. So, and then in that graphical method is what we call a tail to head method. So you draw a resultant vector from the tail of the first vector to the head of the last vector. That is the tail to head method. That's why it's called the tail to head method. You're drawing it from the tail of the first vector to the head of the last vector. So let's see how it looks like. So now you have this guy pushing a cart 10 newtons to the right. So when you use the tail to head method or the graphic method, let's start graphical. Step one is to choose a scale. I'll tell you what that means. So if you're using the graphic method, step one, you choose a scale. What that means is if you go to your ruler is about 30 centimeters long because you draw these arrows with a ruler, right? You take your, you take your ruler, right? And then from your ruler, let's say this is your ruler. Here, say this is 0, and this is 30 centimeters. So what you do is you would say, since I will draw these vectors, when you draw a vector, it'll typically have length, right? From here to there is the length of the vector. So from here to there is the length of the vector. Now what you do, you take your ruler and you say, in my ruler, when I draw this vector, if I draw a vector that is 10 centimeters long, for instance, just as an example, that would be equivalent to 10 newtons, right? So why do you do that? You do that so that if you measure this vector and you see that, okay, all the vectors I've drawn, another one is 10 centimeters, another one is 6 centimeters, another one is 3 centimeters. To your head, that is actually 10 newtons, 3 newtons, 6 newtons, and so on. All right, so obviously when you choose a scale that will allow you to draw the vector so that it's big enough, but also small enough to fit in your ruler. For instance, you can't say by scale, by the way, you would say for every 1 centimeter on my ruler is equals to, let's say, 1 newton. You would choose something like this is a scale. What does it mean? It means this is a scale. This is a scale. So let me take this. Remove this guy. Okay, we have another one here. Good. Okay, now we have that. Okay, we'll come back to that. We are still here for now. So this is a typical scale, right? 1 centimeter on my ruler is equals to 1 newton. So what are you doing here is you're taking the length of the vector and you're drawing it. While drawing the length, you measure it with your ruler. So the scale is chosen arbitrarily. There's no rule to choosing the scale. It's all based on your intuition, right? So as I was saying, for instance, you can't choose a scale that will be outside your ruler because you won't be able to draw that vector. What do I mean by that? You can't say, for instance, let's say you can't say 2.5. No. Let's make an example that is like this. 4 centimeters on my ruler is equals to 1 newtons. You can't do that. Why? Because what you're saying is when you draw a vector that is 4 centimeters long, right? If this is 4 centimeters long on your ruler, because you're using a ruler here, this is 4 centimeters long, and this is equals to 1 newton, not 4, because that's what you said here. You said 4. This is equals to 1 newton. And if you want to go to 10 newtons, it means you must multiply this 4 by 10, right? So that means you would need to have a ruler that can give you a length of 40 centimeters. Now, obviously, this is not possible. Your ruler only ends at 30 centimeters, so you can't draw this one. So the trick here is to choose a scale that will be big enough so that the vector is actually easy to see and visualize, but also it should not be big such that it's a nonsensical vector. You can't measure it with your ruler. Even if you can measure with your ruler, it's just too big. It looks strange, right? So it's all at your own discretion. You choose the scale based on your own intuition and your own common sense. Right, that's how the graphic method works. So let's just finish this example. So let me just say, when choosing the scale, this is an example, e.g. Your vector will be long enough to visualize. But short enough to fit in the length of your ruler. So it doesn't have to be the length of this ruler. It can be in between the length, somewhere in between. It doesn't have to be 30 centimeters exactly, because if it's 30 centimeters exactly, you will have a very long vector that covers your entire exercise book. That's just impractical. You can't work with that. Right. The length of your ruler. Within, actually, let's say within so that we don't confuse you. To fit within. Right. So let's take this example that we already have. Let's say we choose a scale of 1 centimeter represents 1 Newton, right? So if you choose that scale, what that means, it means if you draw a vector that is 1 centimeter, you would have 1 Newton. If you draw a vector that is 2 centimeter, you would have 2 Newton. If you draw a vector that is 3 centimeters, you would have 3 Newton. So this scale is actually easy to work with because you know 1 is to 1. For every 1 centimeter, I have 1 Newton. So now, what if you want 10 Newtons like we are given in the problem? So what you do, it means you would need 10 centimeters. Let's do this. Much better. So this is how the scale would work. What if you chose 2 centimeter equals to 1 Newton? What would that mean? It means if you have a vector that is 2 centimeter, so what if you have a vector that is 2 centimeter on your ruler, it means this would be 1 Newton. If you have a vector that is 1 centimeter, it means this would be 0.5 Newton. How did we get 0.5 Newton? When you take the ratio, you said 2 centimeter on my ruler represents 1 Newton of the vector's magnitude. Okay. So what if I want 1 centimeter? What Newton would this give me? So you solve. You cross multiply, right? 2x is equals to 1. Because when you cross multiply here, you'll get a 1. Therefore, x is 0.5. Why is x 0.5? Because you divide by 2 here, divide by 2 here. X is 0.5. That's why we have 0.5 newtons. Right, so always choose a scale that is easy for you to use. See now, if you choose 2 centimeters, 1 Newton, that might be an issue because now you have to divide, find ratios and so on. But our previous scale, which is this guy, is actually very easy for our problem. We know that we just need to draw 2 vectors. One vector will be having a length of 10 centimeters because 1 centimeter will give us 1 Newton. Therefore, 10 centimeter is 10 Newton. The other vector will be 6 centimeters. Why? Because 1 centimeter gives us 1 Newton. Therefore, 6 centimeter should give us 6 Newton. Right. So that's how it would work. Now, let's continue with our original scale. So, that is easy to work with. This one possible but not easy to work with. Right. So that's what you would do. This is your ruler. And we said it has all those measurements up until 30 centimeters. So for our problem, let's come back and get our problem. Great. Now for our problem, we choose 1 cm is equal to 1 Newton. Meaning right? Therefore, 10 cm will give us 10 newtons. And 6 cm would give us 6 newtons. So that's what you would do. So let's draw these vectors. What you would do is 1 is to the right, right? This guy. Let's draw that guy first. The order does not matter. You can draw them in any order. Doesn't matter really. So vector 1, we draw it going to the right. They said it's going to the right. Right? That's vector 1. And this length is 10 centimeters on your ruler, right? On your physical ruler, not your imagined one. Right now, we are imagining our ruler. We don't have a ruler on this. But your physical ruler, the one that you own, you draw an arrow that has a length of 10 centimeters. So these 10 centimeters means we have 10 newtons to the right. Now, remember what we said last time. We obviously cannot draw the other vector on top of this one because we won't be able to see it. So we just mark a line here. And we know that we can start it here because it has to start from the head of the previous vector going to its intended direction. So the intended direction is to the left. So it means our second vector would go from here exactly at the same position where the head of the last vector ends to right about here. If you do with your ruler, you will notice these two lines will not be of equal length. Why? Because this one is 10 centimeters and the one I just drew now will be 6 centimeters. So there's no way they should be of the same length. Right. Then this would be 6 centimeters. Right? Then once you have that, so now it's time to find your resultant vector. Remember what we said about the resultant vector. It is always drawn from the tail of the first vector to the head of the last vector. So this is the first vector's tail, and this is the head of the last vector's tail. The first vector is blue in this case, which is 10 centimeters. The last vector is red, which is 6 centimeters. So I color code them so that you can see them. Now let's draw the resultant. It goes from the tail of the first vector to the head of the last vector. So what happens now? This is your resultant. Right. So this was vector 1, this is vector 2, and this is your resultant vector. So when you're using the graphical method, you want to know how long is the resultant vector. So what you do is you measure the resultant vector. You would find that what is the length of this vector? You measure right? So between you and I, you should be able to see that if this line is 10 centimeters and the other one is 6 centimeters up to this point, it means the remaining length is 4 centimeters. But you don't have to think like that, because if you have a ruler and you draw these things as accurately as possible, you will get that the length of the resultant will be 4 centimeters. Now take that 4 centimeters and turn it into newtons. We said 1 centimeter is 1 newton. Therefore, since our scale is 1 cm is 1 Newton. Therefore, 4 cm is 4 Newton. Aha. So that means our resultant vector is 4 Newton in magnitude. Now, where is it going? Luckily, the algebraic method will allow us to always know where the resultant is going. It's going to the right. As you can see, we drew it from the tail of the first vector to the head of the last vector, which goes to the right. Therefore, resultant is 4 newtons to the right. So when I was still in grade 10, I didn't particularly like this method, but I had to learn it because you wouldn't know what they would ask for in the exam. They can say specifically use this method or use the algebraic method. So that's our method 2 for the same problem. So what if we chose to use the algebraic method instead? But before we move on to the algebraic method, let's recap how we did the graphic method. So graphic method, step 1, you choose a scale. Scale could be any scale that makes sense to you. By make sense, I mean you shouldn't choose a scale like 1 centimeter is equals to 5 Newton. Because if you do that, for a problem like this, it means you would have a very small vector that's hard to see because you would have 2 centimeters. It will be very, very small. So you choose it such that it's long enough for you to see and for whoever will be marking for you to see. And it's also not too long such that it's longer than the ruler. Right. Sometimes you'll have other vectors. It should be long enough so that you can fit the other vectors as well. And also, it should be long enough to allow you to see the difference between the vectors. For instance, let's come back to this one. You see these ones? The 10 centimeter is long enough for me to see that these two vectors are not of the same magnitude because 6 centimeter is shorter than the 10 centimeter one. So that's what I mean. Right. And then we choose a scale. In this case, we chose this one. 1 centimeter is 1 Newton. Right. So that was our scale. And then after choosing a scale, you take your ruler, you draw. In this case, we needed our vector to be 10 newtons. So you draw 10 centimeters. That becomes 10 newtons. Right? Now, once you have that, you draw the other vector as well. So the next vector, you always draw it from the head of the first vector or the vector before. Remember that rule. Right. So let me quickly give you a recap on that. Whenever you're still drawing vectors, you're not drawing the resultant. If you have a vector going like this and you want to add another one, you have to start it here from where this one ends and you go to where the other one is supposed to go. If maybe you have another one that has to go to the left, but you see it has to go to the left, you just do this because you can't draw it on top of this, otherwise you won't be able to see it. And then you move to the left and so on and so forth. You always start it at the head of the previous vector. How is it different from the resultant? The resultant says, after I've drawn all my vectors, now I can start from the tail of the first to the head of the last vector. Then I can get a resultant. That's the difference. Okay, let's continue. Now, yes, we were recapping. So once you have drawn the two vectors, now you can find the resultant. You always draw it from the tail of the first vector to the head of the last. Then you can measure the length of that resultant and you use your scale to finally find the magnitude of that resultant. Yes, that's how you should do it. Okay, now, what if we use the algebraic method? This one is the one I used to find easy because it's just adding up the numbers. So with the algebraic method, let me add our problem again. Here's my clipboard. Come on. Great. Aha, now we're fine. So with the algebraic method, how does it work? Right, so let's do it like this. What you do with this method is the first step. If you notice here, you are given two directions, right and left, right? So step number one of using the algebraic method, step one, you would have to choose a direction that you call positive. Any direction works, any, up to you. If you think left is positive, that's okay. If you think right is positive, that's okay. There's no rule to choosing that direction. Any direction works. So you choose one direction that you regard as positive. So we have two directions here. We have right, left, right? So let's say we choose right as positive. Excuse me. Yeah, this is a shortcut for positive. I'm just writing it like that, but it means positive. Okay, so let's say we choose right as positive. So what does that mean for left? It means automatically anything opposite this direction will be left, will be negative. Negative. If you choose left, it means right will be automatically negative. If you choose right as positive, it means left will be automatically positive. Negative. So let me say, and vice versa. I forgot how to write vice versa. It should be something like this. You will check it there on your English vocab. Right. Now, vice versa just means the opposite is also true. Okay, so this is the first step. So this means force 1 is 10 newtons and it's positive. Therefore, force 1, let's call it F1, is 10 newtons plus, it's positive. And force 2, which is the 6 Newton one, is negative 6 newtons because it's to the left. Right, notice the signs. Signs, see that? That is negative because we said this guy, left is negative, while right is positive. Therefore, that is positive. So what do you do after? To find the resultant, the graphic method is very short. The algebraic method. Step 2. So you find the resultant by taking the sum of all the vectors that are involved in the problem, and you include their signs. So what does this mean? It means you say F resultant, if you can call it that, right, is equals to F1. Okay, let me do this. F1 plus F2, right? Which is equals to, we said F1 is plus 10, F2 is plus, and then it's minus 6, right? This plus is just this one, right? So if you put this in your calculator, plus 10 is simply just 10. It's just positive 10. And then this is simply 10 minus 6. And it is equals to 4 newtons. Aha, now check that. Tell me if it's not the same as this guy. 4 newtons right there. Now tell me how many steps it took us to get to the answer. Literally just 2. And on the graphic method, it took us, well, I don't know. So this is how the algebraic method works. Now, F resultant is still not complete. It's a vector, so it needs direction. Now we see, since we chose right as positive, and our F resultant is positive, it means it is going to the right. Because it is positive. Let me write it for you. Keep it as simple as possible. Right. Notice in this method, we didn't have to draw it. We don't know how it looks like. All we know is that it has a magnitude of 4 and it's going to the right. We know it's an arrow because vectors typically are always represented using arrows. So that's how you do the graphic method. Simple, right? It's a straightforward method. So when I was still in grade 10, this is the method I preferred. But because in an exam, you have to know both. Make sure you know both these methods. Right. Good. Now let's move on to another problem. Let's check this one. Before we go there, let's do this. And notes. So here's a side note. It is possible for a resultant vector to have a magnitude of, this won't fit. No. Guess what the magnitude I'm talking about is? Type it there, I want to see it. It is possible for a resultant vector to have a magnitude of, let me write it, 0. Right. So we will use our next example to show you how that is possible. See next example. Let's take it and put it there. Now, it says a student applies 3 forces. We've been dealing with 2 forces so far. Now, this student is applying 3 forces, right? We'll use the tail to head, and you can also use the algebraic, but let's use, I'll move a bit faster now because we know how to use the tail to head. So the student applies 3 forces to move a sled, okay? 4 newtons to the right. Okay, 4 newtons to the right, 7 newtons to the left, 3 newtons to the right, and then find the resultant vector. So remember, the order does not matter. Let's color code them. Let's say this will be my red. I'll take this one as blue, and I'll take that one as purple. I hope that's purple. Let's start with the first one. Remember, choose a scale. Don't like this. Looks too red. I'll choose 1 centimeter is to 1 newton. It'll still work for this example. However, this is not a universal scale. It will not always work. You have to choose your own scale. Right, in a different problem, it might not work. Let's say you had, 40 newtons. You can't use 1 centimeter is equals to 1 newton, because then you would need to measure 40 centimeters. And that's not possible with your current ruler. Even if it was possible, it would look nonsensical. Why? Because you wouldn't have a chance to throw 40 centimeters worth of a vector in just a simple exercise book. All right? So it's very important to choose your own scale. A scale can be anything. It can be 0.5 centimeters is equals to 1 newton, anything. So if you see that the vector is too big, you reduce this side, the centimeter side. So instead of 1, you reduce it to maybe 0.5. Usually that typically works for almost any big magnitude vector. If not, you reduce it to 0.2. If not, you reduce it to 0.1 centimeters. Right. Scale can be any scale. There's no right or wrong scale. There's only nonsensical scales and impractical scales. Right. So 1 is to 1 can still work here. So let's throw these vectors. 4 newtons to the right. This means this would have to be 4 centimeters. Right? 4 centimeters. My pen is misbehaving now. Okay, better. And then, right. I forgot to say. What is this thing doing? Edit. Okay, it's fine. Okay, let's do it again. Four newtons to the right. We said this is 4 centimeters, right? And then now we have 7 newtons to the left. Remember what we said? Starts at the head of the last vector. Since it's going to the left, we'll go to the left. Let's use blue for this one. 7 centimeters to the left. This is what my 7 centimeters look like. Notice it's longer than the 4 centimeters. Why? Because 7 centimeters is greater than 4 centimeters. 7 centimeters to the left. Now, three newtons to the right. So you start from the head of the most recent vector and go to the direction that you want, which is to the right in this case. To the right, 3 centimeters to the right should be something like this. That's 3 centimeters. Now, what do you do to find the resultant? From the tail of the first vector to the head of the last vector. So let's do it. Let's put it here. Use your scale to sketch the vectors using a ruler. Okay. Now let me slightly exaggerate it to make sure it's easy to draw everything else. If you draw it with the ruler, it'll be easier to draw. Right now, I'm just exaggerating it because I know conceptually we shouldn't have 7 centimeters being less than 4 in length. So now we have that. Let's draw our other vector. You can draw it here. Let's say this is our 3. Right. Now, from the head, from the tail of the first vector, which is this guy, to the head of the last vector, which is that guy, you draw your resultant vector. So we can do this, and we can do that. So it should move from the tail of the first to the head of the last. That would be your resultant. Which color can I use? Let me use black. From the tail to the head. That is your resultant vector. Right? It started at position 1. It went to position 2. Now, why didn't I draw it to be like here? Let me show. Why didn't I draw it from there to there? Why didn't I do that? From the tail to the head still. I mean, it's still correct. I went from the tail to the head. But why didn't I draw it like this? And I just drew it to be to be horizontal instead of diagonal. The reason for that is we are dealing with 1D vectors. 1D means one dimension. This one, the diagonal one, will be a 2D. So that's not right. So whenever you find yourself drawing 2D, just know you're either doing a very hard problem or you're doing something incorrect. So always have 1D. Right. Let's do this. Yeah, better. That's your resultant. Now what you do, last step, you measure the resultant. That's your last step. The resultant. Good. Let's do that. So the resultant, you measure it using the ruler with your ruler. You will find it to be Zero. 0 newtons. So the reason I drew this arrow, right, because if it's 0 newtons, it means there's no, you can't measure it. It's just 0, 0. It's not even there. Right, so the reason I had to draw it in this case was so you to see in an example where it's not 0, this is how you would draw it. So this means actually that there is nothing here. I don't want to erase it, but let me do this. This means that your thing should actually be copy. This means you were supposed to get something like that. So you were supposed to get something like that. And it actually makes sense because if this guy is 4 centimeters and this is 7 centimeters and 4 minus 7 is 3. So if 3 is going to the other way, you would definitely have a 0. So we will prove it again using the algebraic method, right? So this is what you would have. Like this. Excuse me. Now let's move. Take this guy, move him there. This is our last example. Why is it not moving? Okay, that's weird. Okay. Now, the algebraic method. Okay, it's fine. Let's say we choose left. Because last time we chose right as positive. Just to show you, you can choose any direction. Right. Say we choose left. Now let's come back here. Where is it? Our problem. I want to take it. And put it here. Great. Just great. Aha. So this is our problem, right? So we choose left as positive. So let's highlight it so that we keep it in mind. Left is positive, right? So this guy is left. So it should be positive. And that means right is negative. So let's continue. Negative. Let's go. So therefore, we would have something like this. F1, which is 4n to the right, would be actually minus 4n. F2 would be to the left, so it's plus 7n. F3 is to the right, which is therefore minus 3 n newtons. N is newtons, remember. Now, notice this guy is positive. The other guys would be negative because we said right, sorry, is negative, like this. So therefore this guy and that guy are negative. Aha. What's the resultant now? Now find the resultant. Okay. Therefore, we can say F resultant. You can also call it FR, it's up to you. As long as you know in your mind that that is your F resultant. Because I know you can dread the process of writing F resultant. It's such a long word. Okay, F1 plus F2 plus F3. Right? Good. Aha. F1 is minus 4 plus 7, right? Because 7 is just plus 7. So plus minus 3. So if you punch this in your calculator, you would get that this should be, let me see, 0. Aha. So 4 minus 4 plus 7 is positive 3. Positive 3 minus 3 is simply 0. So you see, this one took us 2 steps. Very quick, we decide the direction we want, and we sum everything else. And whatever direction we get, we choose that as our direction of our resultant. But in this case, the resultant is 0, so there's no need to choose a direction because it's just not there. Everything else cancels out, and then there's no resultant left. That's what it means. So same as the conclusion we reached here. Right. So that is how you would do it algebraically and graphically. And then now, this one I just did it for fun. The last one, you don't have to know how to do such problems because it's 2D. But I wanted to illustrate my point. So let me say, okay, let me move it to the, it's just to illustrate a point. It's not necessarily a problem or a type of thing. Select all, cut. You would have to know off by heart. Okay, so here's how it goes. You have this guy, the textbooks. Okay, it's rotating. I don't know who told it to rotate. Weirdo. Now, we'll only use the head to tail method. We won't use the algebraic method. I mean, we won't use the algebraic method. Illustrative. Okay, won't fit again. Why is it doing that? Nice. Purposes only. Only. Let me write that only in bold so that you don't think, oh my goodness, the exam is gonna chop me because I don't know how to do these things. Don't worry. So a delivery drone experiences the following forces: 4 or 5 newtons east, 3 newtons north, 4 newtons west, and 2 newtons south. Let's throw them. Remember your compass. East is here, west is there. Typically, okay, not typically, but north will always be there and south will always be there. Never mind about those things of true notes and whatnot. Let's just use the grade 3 campus type of thing. Right. Now, so we have that, right? Let's draw our vectors. Ooh. Okay, we don't have to differentiate them, but it's fine. I'll try. F1 goes 5n east. You would obviously measure 5 centimeters if you choose a scale. Right, 5n east. And the other one goes 3 newtons west. Let's say 5 centimeters. Oh, 3 newtons north, sorry. Let's use this guy. It looks so yellow. 3 newtons north would be something like this, right? That's your 3 newtons north. Now, let's say we use 4 newtons west. From here, remember, we always draw it from the head of the previous one. So 4 newtons to the west should be longer than the previous one, but shorter than this red one, because this one should be, this would be 3 centimeters, right? This would be 4 centimeters. And then we have 2 newtons south. Ooh, 2 newtons south is even way shorter. Something like that. Okay, this is a bit too small. Let me try and do it like this. Yeah, you should be able to see it now, hopefully. And then this will be 2 cm, because it's 2 newtons, assuming we choose a scale of, sorry, I forgot to write our scale. Okay, let's not assume, let's say, because assuming it means something else. Is 2 1 newtons. If you're doing geography, you would see you know scales quite a lot, because I know in maps and whatnot they use scales. Now, what's our resultant? Now, this is the point I wanted to illustrate. If you remember our previous exercise, we couldn't draw a resultant like this. We could only draw it like that. Reason being, that problem was a 1D problem. Every force there or every vector was 1D, but this one is 2D. Why am I saying it's 2D? You have 2 directions. Before, we would only have one directions along the same axis here, which is either east or west, left or right. Now we have 2, which is east, west, north, and south. So this automatically becomes a 2D problem. Since this is a 2D problem, it's very much acceptable to draw our results. And from the tail of the first vector, right, to the head of the last vector. That's your F resultant. But you will not have to do this in your exam or anything, unless it specifically said it's a 2D situation, but you won't have to in your syllabus. You'll only do it in grade 11. So now, this is the point I wanted to illustrate. Right. So it is perfectly fine here to draw it like this because this is a 2D problem. But on the previous one that we had, you couldn't draw a resultant like this because it was a 1D problem. So that's the difference. So that brings us to an end of today's lesson. So note, in grade 10, you would only do 1D problems. resultants of this kind. As long as you're in grade 10. Actually, I can move this up there. Great. So that brings us to the end of today's lesson and actually this specific section of physics. On our next lesson, we'll cover a different section. With that being said, thank you guys. Enjoy the rest of your evening. So we're able to do the So today we're able to do the graphical method and the algebraic method. Yep. All right. See you guys on our next lesson.